Now let's examine the basic model, which is sleep and wake up. So assume that we have system calls sleep and wake up. If any process calls the sleep, it will go and get blocked, and if any process calls wake up, it will, one of the blocked process will get waked up. So what I would like to do is, there is a popular example which is called as producer consumer problem. It is the most popular problem. Using this example, we shall examine the sleep and wake up. So now the synchronization mechanism which we are going to see is sleep and wake up. Whenever the resource is not available, which means whenever critical section is not available, the process is going to go to sleep. And whenever the critical section becomes available, which means the process which has just finished using the critical section should check if someone is sleeping, and it will wake up so that that process will get into the critical section. This is the mechanism, right? And now let me tell you how does this consumer and producer problem works. Producer means it is like this. If there are two processes in which one process is producing something, another process is consuming that, then it is called as generally producer consumer problem, which means one process will write something as the output, and the other process is going to read what the first process has written. That could be anything. Either it could be a result of a computation, or it could be something it received from some other process. Whatever it is, the main communication is one process writes and other process reads. The process which writes is also called as writer, and the process which reads is also called as reader, or sometimes it is also called as producer. The process which writes is called as producer, and the process which reads is called as consumer, right? And now in order to read and write, both of them will be using something called as a buffer. Buffer is nothing but memory, right? So I'll explain you how the producer will produce the items, and how the consumer will read the items, and how we can use the sleep and wake up instead of the Peterson solution or any other solution with busy waiting. Now let's see this. Watch it now. So this is the beginning, and this is the last one. First one is hash define n as 100. So what is this? This one is capital N represents the number of slots available in the buffer. So buffer can at any time hold 100 items, and then count equal to 0. So hash define count equal to 0. Here count is, it represents how many items are already present in the buffer. Okay. So first one is, it represents how many number of slots in the buffer, and the second one represents what is the number of items that have been filled up in the buffer. Okay, understood this? Now void parameter, void producer, void in temp. So we are going to use a temporary variable. While true means the producer is continuously going to do this, continuously going to produce the items without stopping. It will stop only when the buffer is full. Now item equal to produce item, which means it is going to instead of item, instead of temp, I could use item here. So item is a temporary variable, and now producer is going to produce item. So this produce item, how it gets produced, that is irrelevant. It is able to produce some item, and that is going to be placed in the item. If count equal to n, what does it mean? Count means the number of items which are already present in the buffer, and n means the total capacity of the buffer. So if both are equal, which means if the buffer is full, then even though you produced an item, you cannot write it in the buffer. Therefore you go and sleep, isn't it? So if the buffer is full, producer cannot go ahead. It has to go and sleep. Sleep until what time? Until there is at least one slot, so that it can produce the item and put it there, isn't it? In case if count is not equal to n, which means count has started at 0 and it has not yet reached 100. So if in case both are not equal, which means there is space in the buffer to put one item, right? In that case, what happens is insert item, which means we are going to put the item into the buffer, and then count equal to count plus 1. So it means that after inserting the item, we are just going to increment the count, indicating that the number of free slots available is decreased by 1, or the number of items that have been filled in the buffer are increased by 1, right? If count equal to 1, it is interesting, see this, if count equal to 1, then earlier count was 0, isn't it? Then there will be a chance, right? There might be a chance that earlier a process which has seen a consumer which wants to read something from buffer might have seen that there is nothing in the buffer because earlier count was 0 and it might have went to sleep state, right? And therefore you wake up the consumer. Okay, don't worry about this part, we shall examine it later. First understand till here, right? Which means producer is going to produce an item, and in case if the buffer is full it is going to sleep, otherwise it is going to insert the item. Just understand till there. Now what's the consumer? What consumer will do is, consumer will initially see if count equal to 0, which means it will check if there is anything in the buffer which it could read. In case if the buffer is completely empty, it cannot do anything, right? Therefore it is going to sleep. So producer is going to sleep when the buffer is full, and consumer is going to sleep when the buffer is empty. Logical. And item equal to remove item. In case if it is not true, which means if count is not equal to 0, then definitely there will be some item in the buffer. Then it is going to remove that item, and then count equal to count minus 1. It is going to decrement the count, which means it is going to consume an item, and after consuming the item, that item is no more in the buffer. So it is saying that the number of items in the buffer are now reduced by 1. If count equal to n minus 1, okay, it is interesting. If count equal to n minus 1 after consuming an element, if there are n minus 1 elements in the buffer, then what would be the number of elements before consuming it? N elements. Now if the number of elements in the buffer are n, then there might be a chance that a producer which tried to write a item into the full buffer earlier must be sleeping. Therefore it is your responsibility to wake up, right? See, it is not always true that a producer will be sleeping, but there is a case, there is a chance. So what does it mean is, after consuming an item, if the current capacity is n minus 1, then definitely before consuming the item the capacity is n, isn't it? Then what is that you are supposed to do? If before consuming the item, if the capacity is n, then there might be a chance that if the producer might be sleeping. Why? The producer might have tried to write an item and he might have failed because the size of the buffer is completely filled. Therefore he might be sleeping. Therefore you are supposed to wake up, isn't it? Okay, and after that it is simply consuming the item. Okay, now watch it here. Here also the same thing, right? So after writing it, see, where is it? After incrementing the count, which means after producing an item, if the count has become 1, then what would be its value before producing it? This value might have been 0, which means there might be a chance that the consumer might be sleeping when it has tried to read a element from the empty buffer, right? Therefore whenever count equal to 1, the producer will wake up consumer, and similarly whenever count equal to n minus 1, consumer will wake up producer, right? So some gate questions possible is when is each one going to wake up the other one? That is one thing. Fine, this is how this producer and consumer works without any conflict in the sense they will not be in an infinite loop. They will just go and sleep and someone is going to wake up. But there is a problem here. If you observe this, the problem is like this. Watch it. Assume that the consumer initially has tried to access the buffer and it found out that count equal to 0. Then it found out that, oh, the buffer is full, the buffer is empty, and it has just read the value of count equal to 0 and it is about to go to sleep, right? And suddenly it got preempted. So what happened? Consumer suddenly got preempted at this point. It is about to go to sleep, but someone has preempted it, right? And then the consumer has came into picture. The producer has come into existence and execution, and now producer has produced one item. Then it becomes, count becomes now 1, and since count is 1, producer will think that consumer must already be sleeping and he will try to wake him up. But the problem is, consumer is not yet sleeping. Consumer is still in the ready queue. It is not in the blocked queue, right? Sleeping means it will go to the blocked state, but still it is in the ready state. So whenever you try to wake up, if a process is in the ready state, nothing will get woken up, right? Then what happens is, this wake up will be wasted. Try to understand it. Consumer is about to go to sleep, but it didn't go to sleep yet. Now producer is thinking that consumer must be sleeping. because it has seen that the count is 1 now, which means earlier count is 0. Therefore he is assuming that the consumer must be sleeping. Therefore he has, he's tried to wake him, but then the problem is he is not sleeping. Okay, if you didn't understand it, let me come back to the terminology of rooms. Okay, now assume that producer is just about to enter the bedroom, and the consumer is just about to enter the bedroom and sleep, but then he didn't go to the bedroom yet. Right now the producer will think that he is already in the bedroom, and he will go and knock the door, wake up, and then he will leave. But actually consumer is not inside the bedroom, right? Therefore he cannot be woken up. He is somewhere else outside, right? Now what happens is, watch it. Now what did producer do? He has knocked on the door and he left. Now what will consumer do? This consumer, when he is scheduled for running, he will now go and sleep in the bedroom. Right now he is sleeping in the bedroom, but then already producer thought that he was in the bedroom and he tried to wake him up, but he was not there. Now he is sleeping. Right now what happens? Producer will think that I have woken up the consumer, and he will keep on producing the items, and after some time producer will also go to sleep, thinking that consumer will wake him up. Right? Why? See this. What happens is, eventually producer will continuously do this, right? And at some point of time the entire buffer get filled, and therefore producer is supposed to go and go to sleep, thinking that consumer will wake him up. Now consumer is sleeping, thinking that producer will wake up, and producer is sleeping in a different room, thinking that consumer will wake up, and both of them are going to sleep forever, isn't it? That is how deadlock is possible here, right? So why do you think that deadlock is possible? The reason is, in the room terminology, producer is thinking that consumer is in his room sleeping, and he knocked outside, isn't it? That is the problem. But okay, see again, the problem is like this. Producer is thinking that consumer is inside the room, right, and he is sleeping, but actually he is not inside the room and he is not sleeping, right? And he has woken up, which means he has sent a signal to wake up, but that wake up signal got wasted, right? And that is the problem. Now in order to solve this problem, you could do a small thing. You think about it. So what could producer do is, instead of directly knocking on the door, he could have checked the room, and he had seen that there is no one inside, isn't it? If no one is inside there, what he would have done is, he might expect that after some time, after he passes, this fellow might go to sleep, right? Therefore what he could do is, in the door knob he could put a tag saying that don't sleep, I am not going to wake you up. If the consumer sees that board now, then he will not go into the bedroom, he will not sleep, and he will be ready, right? So how is that solution implemented here is, whenever you try to send a wake up signal, but if no one is sleeping there, then you maintain a bit, right? Some bit, one small bit saying that don't sleep, right? And whenever anyone tries to go to sleep, they will check if that bit is set. If that bit is already set, it means that producer has already tried to wake you up, so now you don't sleep. So understood this? So what I mean to say is, before you go to sleep, check one more bit, and that bit will be set by the producer in order to say that since no one is sleeping, I am just sending a signal, so you can use this signal at later point of time. It is like giving you a coupon, right? So now if you don't use it now, use it later. Similarly, if you don't have the coupon, then you sleep. If you have the coupon, it means you are already given some wake up call which is wasted earlier, which you could use now. So this kind of using the wake up calls later, that depends on number of consumers, number of producers. Here just one bit is enough. So producer, whenever consumer is not sleeping, he could set that bit saying that I tried to wake up, and next time when you try to sleep, you check the bit. If the bit is set, then you can understand that, oh, he tried to wake me up, and therefore I will not sleep. Okay, that is fine. But now the problem is, this solution works for only one consumer, one producer, right? What if there are n producers and n consumers? Then instead of having one bit, we might have to have an integer which can record how many wake up calls have been made, right? And how many consumers need not go to sleep, isn't it? So if I maintain such a variable, that variable is called as semaphore. So initially this semaphore concept was used by Dijkstra in I think 1965 when this problem first came up, right? Then Dijkstra said that since the wake up calls are going out missing, let us record them so that later we can use them, right? So as like coupons, let us say you went to a restaurant and you are not hungry, but if you have a coupon, you need not have the meals, then you can have it any later point of time. Similarly, if you have a variable which has recorded all the wake up calls, then if you want to go to sleep, just check if there is a coupon available. If there is a wake up call available, then you need not sleep at all, you can continue with your running, you need not get blocked, isn't it? Therefore the concept is like this. Dijkstra proposed a solution saying that record all the wake up calls in an integer and keep on incrementing it if there are lots of consumers, right? And whenever any consumer tries to go to sleep, let him consume one wake up call, which means he will decrement that integer, right? And now after decrementing the integer, and whenever the increment integer becomes 0, it means there are no more wake up calls which are available, therefore you go to sleep, right? And that concept is called as semaphores. So semaphores has been introduced in 1965 in order to solve this problem, right? Let's talk about semaphores in detail. I think you understood this, and one more thing, semaphores need the support from operating system. You cannot implement it without operating systems support, right? So even though we are going to see some solutions which does not have busy waiting, but they need the support from operating system. And anyway, all the modern operating systems, they all are supporting semaphores. Okay, anyway, I'll show you with examples how semaphores work. It is very easy, right? And it has a lot of variables in gate also. Let's look at it in depth. Okay.